In this video, we're going to talk about circular motion and in particular, linear and angular speed. So we've talked about speed before. We know the formula that distance is equal to rate times time. So if we want to know speed, that'd be the rate. It would be distance divided by time. So here, what's a little bit different is that we have objects moving in a circular path. So we have an object that's moving around a circular path, and in this case, the distance is going to be an arc length, right? Because we have an object moving along a circular path. So an arc length, we just learned, is equal to r times theta. So if we have something that's going in circular motion, the linear speed is going to be the arc length divided by time, or r theta divided by time. So let's do a couple of examples. We're going to look at example 14. Here it says the second hand of a clock is 6 inches long, and we want to know the linear speed, and we're given units of inches per second of the second hand of this clock. So I'm going to draw a clock. So a clock has a circular face, and we're going to have some second hand. We're going to assume it's coming out to the edge of the face of the clock. And then we know that the second hand is 6 inches, and the second hand is moving clockwise around the circle. So the linear speed, we know that the second hand travels one circumference in 60 seconds. That's what a second hand does. So what's the circumference? The circumference is equal to 2 pi r, and we know that goes in 60 seconds. So the linear speed here is going to be the circumference, 2 pi, the radius is 6 inches per 60 seconds. So that's our linear speed. Let's simplify this. We can divide 60 by 6, so cancel that out, and then we'd have 2 pi over 10 inches per second. We can divide 10 by 2, so it would be pi over 5 inches per second, and as a decimal approximation, that's 0.628 inches per second. So that's the linear speed of the second hand. In part B, it says, how far does the tip of the hand move in 15 seconds? So there's two ways that we can think about this. The first way, we can say that distance is equal to rate times time. And here we know the rate. It's 0.628 inches per second. And then in 15 seconds, we can multiply this by 15 seconds. That will give us how many inches it travels, which would be 9.42 inches if we multiply that out. An alternative way to do this is if we hadn't just calculated the linear speed, we could simply say that the second hand in 15 seconds travels 1/4 of the circumference in 15 seconds. So we can figure out the circumference and divide it by 4. So we would have the circumference 2 pi r. In this case, r is 6 inches over 4. So this would be, let's divide out a couple things. We can divide 4 by 2. So we'd have 6 pi over 2, or 3 pi inches. And if we multiply that out, we get the same thing as above, about 9.42 inches in 15 seconds. At the bottom of the page, there's a formula for angular speed. And what it says, angular speed is a measure of some angular displacement per some unit of time. So it's important to understand that angular speed is only talking about rotation. It's not talking about a distance traveled around a circular path. If you want, you can use this formula, which is angular speed is some amount of angular rotation per unit of time. Theta is in radians. I usually do not use this formula. Instead, I will solve these problems by converting units. Okay, so note, linear speed is the measure of distance traveled per unit of time, so that's some arc length. linear speed is equal to the radius times angular speed, provided that angular speed is in radians per unit of time. I don't recommend using this formula. So on the next page, I'm going to show you how I recommend that we solve angular speed type problems. But remember, angular speed is just amount of rotation, not a distance traveled. So let's flip to the next page. So here's an example. We have a circular mobile above a baby's crib that makes 5 revolutions per minute. So 5 revolutions per minute, this is an angular speed. It's just talking about how much something turns per unit of time. We're not traveling any linear distance like feet, inches, and seconds. There's a T missing here, so I'm going to put that back in. So part A says, what is the angular speed of the mobile in radians per second? So radians per second is also an angular speed. So we're going to convert from one unit of angular speed to another. And we're going to do this like that homework that I had you do where you learned about factor label. So we have 5 revolutions per minute. That's what's given up here. And we want to convert that to radians per second. So that's our target. So we're going to use whatever conversion factors we need to convert from revolutions per minute to radians per second. So the first thing, you can do this in any order you want. I know in 1 minute there are 60 seconds. And now we've got our seconds. And now we have to get from revolutions to radians. So we also know that in 1 revolution, there are 2 pi radians, because that's how much it is to get around a full circle. And here we can go ahead and we can cancel out the revolutions, and now our units are in radians per second, which is what we wanted. And then we'll simplify this. So if we multiply across the numerators, we'd get 10 pi over 60. And if we simplify this, we get pi over 6, which is about 0.524 radians per second. Okay, so we converted from one unit of angular speed to another. Letter B says, how fast is a toy 9 inches from the center traveling in feet per second? So this is a linear speed, right? We're talking about some distance traveled per unit of time rather than an angular measure of rotation. So what we have is some object that's 9 inches from the center of the mobile, and then it's traveling around this. Okay, in these problems, what I recommend is we just start with what was given. So we were given an angular speed of 5 revolutions per minute, and now we want to convert this to feet per second. So let's do conversion by conversion, see how we can convert this. So we want to get from minutes to seconds. So we can go ahead and we can say in 1 minute, there are 60 seconds. So we've converted minutes to seconds. Now we have to get revolutions into feet, okay? So the key conversion here is in each revolution around this circle, the toy travels 1 circumference. So I'm going to write that over here. So each revolution, toy travels the circumference. That's going to be a key conversion. So in a revolution, the toy is going to travel 2 pi r. In this case, r is 9 inches. So this is the circumference. So now we have converted from revolutions to inches. And finally, we need to get from inches to feet. So I know in 12 inches, there is 1 foot. And now our units are appropriate feet per second. If we multiply this all out and simplify, what do we get? This turns out to be 5 times 9 is 45 times 2 is 90. So 90 pi over 12 times 60. And if you simplify all this, it turns out to be pi over 8, which is about 0.392 feet per second. Part C is almost the same problem, except here the toy is only 6 inches from the center instead of 9. So we've got a toy here. It's 6 inches from the center. So the problem is identical. The only thing that's going to change is the radius of the circumference. So we can do the same problem again. We're going to start with 5 revolutions per minute times in 1 minute. There are 60 seconds times in 1 revolution. There are 2 pi, in this case, 6 inches per revolution. Remember, that's the circumference. And finally, we have to convert from inches to feet. So there are 12 inches. That goes in the denominator per 1 foot because we need to cancel this out. And if we simplify this whole thing, it turns out to be pi over 12 feet per second, which is about 0.262 feet per second. Letter C says, what is the linear speed of a toy directly at the center in feet per second? So here we have a toy that's directly at the center, which means r is 0. So if we think about our previous calculation or just what's happening, if a toy is directly at the center, so a toy at the center is only rotating. So is not moving linearly. So, and if we were to do the calculation, we'd have 5 revolutions per minute times 2 pi times 0 inches per revolution. And then we'd have, in 1 minute, there are 60 seconds, and we could continue on. But the key thing here is that we've got 0 here, so this is going to turn out to be 0. So this is going to be 0 feet per second. I didn't do all the conversions here. I guess we would still need 12 inches per 1 foot. Okay, so something at the center does not have linear speed. It only has angular speed. Okay, a couple of notes I'm going to read to you at the bottom. Notice that even though all the toys on the mobile maintain a constant angular speed, right? They're all going 5 revolutions per minute. The linear speed increases the further the toy is from the center, right? The toy that was 9 inches out was faster than 6 inches out in terms of linear speed. Okay, while a toy at the center has angular speed, but 0 linear speed because it only rotates. Then an interesting note, this effect is extremely important in several different areas. Tire differentials, to name one in particular. When you're making a right turn in an automobile, the tires on the passenger side of the car must travel less distance than the tires on the driver's side. Right? So if we have a car that's turning, we have 2 sets of wheels. So if you're making a right turn, these outer tires, these travel further. And these travel less distance. So in order for the car to stay in one piece, in order for the car to stay in one piece, a consequence is that the outer tires must rotate faster than the inner tires. This is precisely what happens. The car's axle, so there's an axle here, requires differentials to allow the tires on the same axle to travel at different speeds. So you can explore it more at the website listed in the notes.